Mr. Corsi here. In this video we're going to look at multiplying complex numbers when they're written in polar form. So just a wee reminder of polar form. Here's a complex number Z1 on the Argand diagram. Here's its polar form. This number 2 gives the modulus. It's the distance the point is, a complex number is from the origin, and 0.28 is the angle that's shown, positive angle round from the real axis. So as this complex number moves around, you can see the modulus and the argument changing. Now, the argument and this demonstration always involves the principal value of the argument. So when we go right round to say -2, for instance, you can see that argument's pi. And when we go to 1, the argument is 0. And that argument is negative pi upon 2, which is approximately negative 1.57. But as we come round to say -1, as soon as we reach -1, it immediately jumps back to pi. So the principal value of the argument goes from negative pi all the way round to pi. Includes pi, does not include negative pi. So let's do a few familiar numbers. Suppose we use the number 3 first and look at the polar form. There is the modulus. Z1 is certainly 3 units from the origin. Cosine of 0 is 1. Sine of 0 is 0. So in brackets here we would just have the number 1. 3 times 1 is indeed 3. Let's move to 2i. Modulus of 2i is 2. That distance from there to the origin is 2 units. The angle, pi upon 2, if you half pi, you'll get approximately 1.57. The cosine of pi upon 2 is 0. The sine of pi upon 2 is 1. So we get 2 lots of 1i, which is 2i. So that ties up. If we do this to negative I, the modulus of negative I is 1. It's a distance 1 from the origin. The principal value of the argument is negative pi upon 2, approximately negative 1.57. So cosine of negative pi upon 2 is 0. Sine of negative pi upon 2 is -1. So we have 1 times, in bracket, we'll get I times -1. So that's 1 times negative I, which indeed is negative I. And one final one, let's move round to -2. Modulus is 2. Principal value of the argument is pi. Cosine of pi is -1. Sine of pi is 0. So we'll get 2 times -1, which does indeed give us -2. And maybe one last one. There's 1 plus I. And by Pythagoras there, the modulus would be √2, which is approximately 1.41, and the angle is pi upon 4, which is approximately 0.79. And cosine of pi upon 4 is 1 upon √2. Sine of pi upon 4 is 1 upon √2. So when you multiply both of these by the factor √2, they will cancel out and you'll end up with 1 plus I. So that all works out very neatly. Let's introduce a second complex number. Let's move this first one to have a modulus of 2. It's easier to see what's going on then. And we're going to multiply these 2 complex numbers together. Here's the result. And here's the new modulus and the new argument. And I think we can see that there's a multiplicative thing going on here. Twice 0.96 is 1.92. And there's an additive thing going on here with the arguments. 0.96 plus 0.33 does give us 1.29. So it would appear that we multiply the two moduli to get the moduli of the product, and it would appear that we add the two arguments to get the argument of the product. Let's now try and prove that. So let's take a complex number Z1, which has modulus R1 and an argument θ1. And we're going to multiply that by Z2, modulus of R2, an argument of θ2. So Z1, Z2, their product. We're multiplying this by this, by this, by this, so the order is not important. By the associative law, we can reorder the multiplication, so we get R1 times R2, and we're left with a familiar setup of having to expand these two brackets, and we'll use the good old technique of firsts, outside, insides, last to expand these two terms. So we have R1, R2. Now we're going to have a real part and an imaginary part of the resulting complex number here. Real part comes from cos θ1, cos θ2. That's the firsts. The outside 2 has an I in it when you multiply them. The inside 2, when you multiply them, has an I. So the second part of the real part of the product would come from the multiplying the two last terms in the brackets. And we have an I times an I being a negative 1 times sine θ1 sine θ2. So that there is the real part of the resulting product, and the imaginary part will come from these outside 2 and these inside 2. And I'll start with the inside 2, I times sine θ1 cos θ2, sine θ1 cos θ2. And the outside 2 will give us cos θ1 and sine θ2. Now you might have been looking at these and remembering a formula or two formula, and you'd be correct to do so. This first one, cos, cos, sine, sine, appears when we expand. It's the addition formula, cos θ1 plus θ2. Remember the pattern when you expand this is cos, cos, sine, sine, and the cosine addition formula, the plus would change to a minus. And then the imaginary part, the sine, cos, cos, sine pattern comes from expansion of sine θ1 plus θ2. You expand this, the pattern is sine, cos, cos, sine, and the plus sign stays as a plus sign. So we've ended up with a complex number. Let's compare it with r cos θ plus I sin θ. And you can see that the modulus r is r1, r2, and that the argument θ is θ1 plus θ2. So we have a multiplication going on. The modulus of the product of two complex numbers is the product of their moduli. That's a multiplicative property. So that's the moduli with the multiplication. Then we've got an argument of the product of two complex numbers is the sum of their arguments. That's an additive property. So that's what we'd seen in the demonstration, and that's what we've proved here. So now time for you to get involved. If you stop the video and try this example. So we'll start this as we should always start problems like this, by drawing an argand diagram and pinpointing exactly where these complex numbers are. So we'll start with Z1, negative 1 plus root 3I, 1 to the left, root 3 up. And then second stage is to create a right angled triangle. So we'll draw the associated vector, if you like, from the origin up to the point. Then there's the vertical distance there. So we can now put in lengths for this triangle. There's 1 and root 3 and 2. And remember, this is half of an equilateral triangle. So that angle in there is pi upon 3. Therefore, the principal value of the argument of negative 1 plus root 3I will be 2 pi upon 3. These must add up to pi. So we've got this polar form. The modulus is 2 and cos 2 pi 3 plus I sine 2 pi 3. 2 pi upon 3. Now we'll tackle Z2. 3 root 3 minus 3I. So we go along 3 lots of root 3. Root 3 is about 1.7. Down 3. And again, we'll make up a right angled triangle. And we can now put the lengths in. That's 3 root 3 on that side. And that's 3 on that side. And the hypotenuse, well, we'll take the square root of 3 root 3 squared. That's 3 3s are 9. Root 3 times root 3 is 3. 3 9's 27. And then 3 squared 9. That's root 36. So there's 6 for the hypotenuse. And once again, there's an equilateral triangle in here. It's actually 3 times the one we had earlier. So 1, 2, root 3. This is 3, 6, 3 root 3. So that angle is negative pi upon 6 this time, half the pi upon 3. That's the principal argument. So we've got modulus of 6 cos negative pi upon 6 plus I sine negative pi upon 6. So let's tackle part A of the question now that we've got the polar forms. We're trying to evaluate Z1, Z2. So we're multiplying these two together. Now remember, the moduli we multiply, the arguments we add. So it's a fairly simple task to do this. Mind you, 2 pi upon 3 plus negative pi upon 6. I think we'd maybe better think in terms of sixth of pi. So multiply top and bottom by 2, 4 pi upon 6. 4 lots of pi upon 6 minus 1 lot of pi upon 6. Well, that will give us 3 lots of pi upon 6. And a factor of 3 top and bottom cancel pi upon 2. So we've got cos pi upon 2 after we add the two arguments together, plus I sine pi upon 2. And remember, cos pi upon 2 is 0, and sine pi upon 2 is 1. So we have 12 times I. So that's Z1, Z2 evaluated using the polar forms. Let's try to do B, Z1 squared. So we have to take 2 cos 2 pi upon 3 plus I sine 2 pi upon 3 and multiply it by itself. Now I'm writing it out in full so that we can see exactly what we're doing here. So the moduli multiplied, 2 2s of 4, and the arguments added, 2 pi upon 3 plus 2 pi upon 3 is 4 pi upon 3. Now you notice that is not a principal value of the argument. We'll go into that in detail in the next video. But there's what we've got, and to evaluate that we need to look at the value of cos 4 pi upon 3. So 4 pi upon 3 is in the third quadrant, pi plus pi upon 3. That's the third quadrant. So we're dealing with an angle of pi upon 3 in the third quadrant. Now we know that sine pi upon 3 is root 3 upon 2. And we know that the cosine of pi upon 3 exact value is 1/2. So since we're in the third quadrant, both of these will be negative. It's only the tangent that's positive in the third quadrant. So we get 4 times negative 1/2 minus I times root 3 upon 2. So both negative, negative 1/2, negative root 3 upon 2. And multiplying out by the factor of 4 gets us negative 2 minus 2 root 2. Sorry, 2 root 3 I. And there's our final evaluation of Z1 squared. So that's Mr. Carsey signing out, and I hope you enjoyed the video.